Hello, everyone. Welcome to the Mining Munch. Mining Munch Network is a space for you to share your knowledge and ideas among mining professionals. We have a variety of topics for everyone. So I welcome you, and please share this space with others so we can grow our community. In today's episode, we are going to talk about geostatistics. This is a very hot topic in the mining industry, and for that, we have invited Dr. David Machuca, who is joining us today from Toronto. David is a doctor from the University of Alberta in mining geostatistics, and he has extensive experience in resource estimation.
So let's talk about the change of support program. So everybody may have heard about George Matheron, one of the founders of geostatistics. In a paper published in 1984, he stated that the most important problem of geostatistics is the change of support. It obeys two principles. As the support increases, the mean remains constant, the mean grade, that means, and the selectivity is distorted. Blessed souls, the mining geostatisticians, they don't need to deal with diseases or catastrophes or stuff like that. Just change of support. That's the worst problem we have. Here is Professor George Matheron. And that's a citation from one of his papers from 1984. I just explain it. So some definitions before going forward. Just to be everybody in the same page, we will refer to support as the volume and tonnage associated to a grade. A grade doesn't exist as a point. It's always a volume of material, of rock that contains that grade. As miners, we are worried about mining selectivity, which is the capacity of discriminate between ore and waste. What's ore? Whatever rock that has a volume of rock that has a concentration of a metal of interest that's high enough to justify the extraction of the profit. And we cannot mine small volumes, very small volumes. We cannot mine with a teaspoon. And so we need to define a selective mine unit, which is the minimum volume that we can mine. It will be basically related to practical constraints, operational constraints, like the mining method and the machinery we will use to extract the material. Well, selectivity is not stated directly in the definitions of mineral resources, such as the CIM definition standards. But if you read between lines, these definitions talk about selectivity. So mineral resources is a concentration in such form or grade or quality or quantity that there are reasonable prospects for eventual economic extraction. And any estimate should be reported at a cutoff grade. And all the estimates should be related to the mining and processing methods, etc. So there is the issue of selectivity is implicit in this definition. So therefore, selectivity is a main concern in the definition of resources and later in their exploitation. But let's put in perspective the challenge of change of support. This is a vein that was And actually, it's not a vein, it's a model that represents a vein. It's one of the domains of a gold deposit in Mexico. And it's quite typical. And it's not a, it's actually considered as a well-drilled vein. And the total volume that has been reported is around 11 million metric cubic meters. But if we compare to the volume of samples, assuming a diameter of HQ is just a very small fraction of a cubic meter. For a SMU of 3 meters times 3 times 1, we will have 9 cubic meters. We see the ratio between the volume of SMU and the volume of the sample. We are having a ratio of 3,000 to 1, pretty much. And if we add up all the intercepts in the vein, we have a total length of 1,200 meters, which amounts for about 4 cubic meters of material that has been sampled. If we divide the total volume of the vein by the total volume of the samples, we will have like a ratio of almost 3 million to 1, 3 million cubic meters to 1 cubic meters, or 0.36 cubic meters of samples for each million cubic meter of mineral. Yeah, if you show this to a classical statistician, he or she will say that it's nuts to come with any inference from this quantity of samples, that the only solution is to sample more. But we have Geostatistics that talks about spatial continuity. It's a great help when doing spatial inferences. And before that, we have geology. So we won't talk about geological constraints or controls this time, but it's important to keep in mind that without geology, the task of inferring the quantity and quality of the metal of interest in this vein is pretty much hopeless. Okay. Selectivity. So we can have, we can look at selectivity from the long-term point of view or the short-term point of view. In the long term, when we report resources, we're interested in getting the tonnage and the grade above cutoff right. We never know this red line, at least not in the early stages of the deposit. We may know with some degree of precision later when we have very dense samples, and that will be the concern of the effect of information that we'll talk later. But the aim of reporting long-term models is mostly global accuracy. By global accuracy, I mean to match as much as we can the true grade tonnage curve, or to close this gap that we see between the estimates and the true grades. In the short term, for models that are ready for production, to discriminate block by block what's ore and waste, we want to reduce the misclassification. So this, the number of blocks that are misclassified as waste or misclassified as ore should be reduced. Ideally, the slope of regression between the estimate and true grades should be pretty much 45 degrees. But we don't know the true rates, not even when we are about to mine the blocks. So this remains still a challenge. And we have indirect methods like grading quality measures that help us to reduce this or to improve this slope of regression, despite we don't know the true grades. Now the change of support. Here I have an exhaustive realistic image. Actually, it comes from a satellite image of a portion of the jungle in Colombia. I imported it as a raster image, separated the red, green, and blue colors, and then made some transformations to mimic some metal grades, let's say silver. It's a 2 megapixels image, so it's 2 million pixels. And then let's see what happens if we reblock from pixel to pixel. Let's talk about meters just for simplicity. So from 1 times 1 meters to blocks of 10 times 10. Here at the bottom are the corresponding histograms to each image. That and the image is reblocked or upscaled. So in a succession of block sizes from 10 times 10 to 50 times 50, 200 to 200 to very huge panels of 600 and 600 meters. As we increase the support, please notice that the mean is constant. But what changes is the standard deviation. Standard deviation comes from around 1100 to just 100 for these big panels. Why is that? Well, the mean doesn't change because the grade is going nowhere. All the metal is still there. So in average, it's still the same. But block per block, high grades and low grades are averaging off. So dilution is happening. So high grades become diluted by low grades, and low grades get mixed by high grades, and everything starts converging to the average. Therefore, the variability, the difference between the square difference between blocks and the average, the block grades and the average grade is smaller, and so the standard deviation is reduced. And what happens if we see this in terms of recoverable tonnage, average grade, and recoverable metal? So we see that for the small blocks, 1 times 1, as we go with bigger blocks, we will increase the tonnage, recoverable tonnage, for the lower cutoffs, but not for the higher cutoffs. For the average rate, as we increase the support, the average grade above cutoff, this is above cutoff. Look at the origin, the average rate is still the same, but above cutoff, the average grade will become lower. So why is that? Because first, for the tonnage, we have bigger blocks that still are above the cutoff grade, but because they are bigger, they contribute with more material. For the grades, now our high grades are diluted by low grades, so they go lower. Overall, for the recoverable metal, for the lower cutoffs, we can increase the recoverable metal but for the higher cutoffs, the recoverable metal is decreasing because it results in much more dilution, much more waste that's included in the blocks or panels, and so the panels are less prone or less able to be above cutoff. Now let's compare how our estimation methods, particularly kriging, perform by reproducing the correct great tonnage curve at a bigger support. Again, we have this exhaustive data set that I've sampled in a mesh of 2 meshes. One is 25 times 25, and another mesh, I think, is 100 times 100 meters. And using these samples, I create I use kriging to estimate a point support. As we can see, the first you may notice is that the estimated grades look way more continuous than the real image, in the real data, and that's reflected also in the histogram. Despite we are estimating at the same support as the image, as the exhaustive data, we cannot reproduce the variability, and that results in a lower variance. So the difference between 1100 less 391 will be the missing variance, and we see this missing variance as a reduced, as a more compact histogram. In terms of the great tonnage curves, we can see that there is despite we are talking about the same support, there is increase in tonnage and a huge reduction in the average grade above cutoff. It's like we already applied a change of support. Well, now let's do block estimation. So what's this powerful notation saying? Just that we are just when we are estimating a block, we are estimating every little differential of volume in this block, and then averaging up to obtain averaging up the grades estimated for every little volume to obtain the average grade of the block. Well, computationally, you cannot go to infinity. You cannot do an integral, so you use sum, and the sum depends. The terms of the sum depends on the discretization of the block. The famous discretization you may have seen in the software you use. So, without getting into details of how the ordinary block kriging works, yes, let's recognize that there are 3 parts in the block kriging system. One is that it has the variance of covariances between the data. This is the first part. The second part are the solutions of the kriging weights. And the third part, in the case of the block estimation, has the average variogram between the data. The U1, U2 are the data points, and the block. So it's like calculating the variogram between this data point, data location, and different locations between the block. And again, it can be approximated by a sum instead of an integral. Okay, let's see now what happens if we compare 2 block grades. If we upscale the point scale or small scale estimates to blocks that are 50 times 50 meters, what happens in the So let me see if I can use a. I can use a pointer. Or there is a spotlight. No. That's okay. Spotlight. Yeah, here at the bottom is the an estimation using at the left bottom a block scale at 50 times 50, but not using discretization. So it's just one point per block. It's like we're estimating single points within the middle of each block. And here we just discretization, 50 times 50. So an important thing to note is that the rate is the true block rates. If we upscale the block estimates, the point estimates, this one, to the same support as the block estimates, we pretty much obtain the same tonnage, the same grades, and the metal. That just says that the block kriging is working. It's working in the sense that we are able to estimate the block grades consistent, not truthfully, but consistently to the change of support. And here we have in green the estimates that are not discretized, and we can see that the recoverable tonnage is the curve is way different of the true tonnage. Same for the average grade and the recoverable metal. So the message from this slide is we always need to use discretization. Okay. Why you cannot move? So it is frozen. Okay, there you go. Here, well, now if we compare the point estimates with the block estimates, we see that the most part of the smoothing, or most part of the change of support effect is taken care by the smoothing, or the inherent smoothing of kriging. It's just this little gap that's the contribution of moving from point kriging to block kriging. But still, if we see the previous image, yeah, we are still a little bit far from the true tonnage, especially for high grades. Okay, now we are seeing a little bit of heavy maths, and I hope there are no minors in the audience, because we'll see some obscene shapes like double integrals, but not yet. So again, the relationship between volume of variance. So the average grade remains constant. Yeah, the standard deviation is reduced, and in an extreme, if we just have one block or one big panel for the whole deposit, we want our standard deviation is 0. And how does the standard deviation changes, or the variance changes? Will be dependent of the size of the change of the new support, the bigger support, the spatial continuity. We'll see a little bit more about how the spatial continuity affects the change of support, and the reblocking process. Oops. This is a Krish relation of the distributor of variance. We have this small box, And we have the variance of blocks within the domain. D represents the whole domain. 26 or almost 27,000 is the variance. Now we reblock the small blocks within panels, each one containing 4 blocks. We have here the grades, and we calculate the variance of these panels. The variance is reduced to 15,000. And then we calculate the variance of each group of 4 blocks within each panel. So here are the variances. This is an exercise that can be done in Excel or in a spreadsheet. And then we take the average of all these variances within the blocks or the panels, sorry. We get 11,000. Now, if we add the average variance of the blocks between the panels and within the panels with the variance of the panels, we will obtain the total variance of the blocks within the domain. That's a nice relationship, but it becomes very useful. So, but we can, but in practice, we don't know the true grades. So how we can estimate the variance of the blocks within the panels and the panels within the domains, etc. So the first can be demonstrated that the variance of points within the volume, it's equal, or it can be approximated to the average variance or multiple points, ideally all the points, multiple points within this volume. That's known as the average variogram or gamma bar. So we have 2 points, do U prime, do U double prime. We calculate a variogram that is averaged with another pair of points within the volume, etc. And we obtain the gamma bar. And the same can be done with the volume. So we have different volumes, and we can calculate variance between volumes, small volumes or SMUs, within the big volume of the panel. And developing the previous Krish equation, we can find this relationship. Expressed in variograms, so the variance of the sample within the domain is equal to this variance of the samples within the SMUs plus the variance of the SMUs within the domains. So we can plug here. So this equation here, this comes, oops, sorry. This goes here. Like this goes here. And this goes here. If I'm not, yeah. And so we can have this relationship between the variance between the variance of the samples within the SMUs are equal to the average variogram within the SMU and the variogram of a sample and itself. But the variogram for a sample of itself at 0 distance is 0. and the variance, average variance of within the domain of it's equal to the variance of the samples within the domain, or just the variance of the data. How do I delete these lines I just created? I'm not used to zoom, so yeah, there you go. Okay, so once we know the variance of the SMUs within the domain and the variance of the data within the domain, we can define this variance reduction factor as the ratio between the both. And by using the Krish equation, relation within this equation, we can find this relationship for the variance reduction factor, which is saying that the variance reduction factor that expresses how much the variance will change from one support to another, particularly from the point support to the SMU support, it's given by 1 minus the average variogram divided, the average variogram within the SMU, selective man units, divided by the data variance. And this is a very useful factor that help us to forecast the effect of the change of support in your great tonnage curve. Let's see this variogram model, and you don't need to look at the parameters, but you can look at the variogram map, at the variogram models. This variogram model is one fitted to the data I just presented before, scattered data set sample from the exhaustive image. And we can see here that as the block size increases, the gamma bar, the average variogram increases. Why is that? Because if we are working with a block that's 10 by 10, we are around this distance here. Okay, and all points within that SMU or block will be separated by less than 10 meters. And so if we calculate the average variogram, will be around 0.55, and so on. For 50 meters, all points will be around between 0 and 80 meters, and our average variogram may be around here, which looks a little bit higher, but it's just an average. As an average, there will be more points that are far away, more combinations of points that are far away than close by. So therefore, it tends to go to the higher end, and so on for 200, for blocks of 200 meter size and 600 meter size. Here is we are using a standardized variogram, so it's standardized by the variance. So this F factor becomes just 1 minus the gamma bar. So the F factor goes down, and that expresses, if we multiply the F factor by the variance, that expresses the proportion of the variance that will be will result after the change of support. Okay. So this variance reduction factor can be used in different ways, in different change support models. The first one is the easiest one, is the affine correction. And it's just based on a quantile correction. So if you have here the grade that corresponds to the P50, let's say, we multiply the square root of the variance reduction factor times the difference between the P50, the grade that corresponds to the median grade, minus the mean, the average grade, and we restitute the average grade to keep the grade constant. And that will be the corrected quantile. The problem with this method is doesn't work well for if our distribution or change of a variance correction factor is too small. So it doesn't work well for any of these cases. And the variance correction factor or variance reduction factor becomes small with our data is very skewed. So for very skewed data sets, it doesn't work well. And you can see the result here that it grossly overestimates all the low grades. And it doesn't do a good job for the other grades either. We're not seeing the maximum value here, but it also can introduce artifacts in the maximum values. So it works well, this affine correction, when you're dealing with grades that have a histogram that's quite symmetrical and not very skewed, not very stark. The second method is the indirect log normal model. It works much better. It goes in two stages. So first is a first quartile correction using these two quantile correction, these two factors. I won't go into details. There is no time for that. And the second, but it's good to know. And the second correction stage is another quantile correction that divides the average grade by the grade that average grade that resulted by this correction that can be distorted. So with that, it's the preservation of the average grade is assured. And the third method is the most sophisticated. It's a discrete Gaussian model, and I won't go either in details. It's the time is quite short to explain. I just want to explain to tell you that it's based in the fitting of the Gaussian transformation, in the fitting of the correlation between original data and Gaussian transforms using Hermite polynomials. So these Hermite polynomials are polynomials of different shapes depending on the grade of the polynomial. So the higher the grade, the more complex will be the grade. We use a combination of those polynomials to fit any kind of curve. In this case, the relationship between original grades and normal score transformed grades. Once we transform the grades into normal scores, we have a nice Gaussian distribution that can be easily manipulated using the variance reduction factor. So the histogram is adjusted in Gaussian space and back transformed. And here is the result. So the red one are the true grades, and let's see how it works. So the fine corrected doesn't work very well. The indirect log normal corrected works quite better. And the corrected diffusion model, I would say, works slightly better than the log normal case correction in this case. In this case, in some other data sets, or if you have more abundant data, you have a better knowledge of your variogram or of your original histogram, it may work way better than the other methods, this discrete Gaussian model. Now let's see quickly on how Gaussian simulation can help us to forecast the right great tonnage curve. A quick overview of the difference between estimation and simulation. So estimation, we do block support estimation, as we just saw. Estimation is aimed at local optimal estimates. So we are trying to approximate, to reduce the error, estimation error between the true and the estimates, the true rate and estimates. For simulation, well, some simulation methods can incorporate some direct block support simulation, but mostly it's done in point support, and that's because we want to reproduce the sample histogram and the variogram too. So by reproducing the sample histogram, then in our simulated cells, the grades in the simulated grades, then we can just reblock at any block support that we want to. Well, the simulation doesn't result in just a single model, but various models that are called realizations, and then we can upscale to different supports. So you see, and different realizations for the same data set, but all are similar but not equal, are slightly different. To the same data set, I have fitted these variants. A high continuity variogram using a Gaussian variogram, model, a zero nugget effect, a mid continuity variogram using spherical variograms with a small nugget effect, and a low continuity variogram using a high nugget effect and exponential models. And so we can see how the variogram impacts the pattern that we reproduce in the realizations. This is just one simulated model. Despite this difference in the pattern, the spatial distribution, all this, the histogram of all these simulated values are pretty much same, and all of them are very close to the true rates histogram, which is the red line. But when we upscale them, again to a 50 times 50 block size, we see that the model resulted of a low continuity variogram results in a lower variance than the model that we built using a high continuity variogram, which results in a higher standard deviation of variance. So the less continuous is the spatial distribution of rates, the stronger will be the change of support effect. And that can be seen in the great tonnage curve. So the high continuity, the one that corresponds to the Gaussian variogram, the distortion of the curve is much more pronounced than the distortion in the blue lines that corresponds to the low continuity variables. Why is that? Because when we have low continuity, we will have more mixture of low and high grades. So when there is more mixture of low and high grades in the same location or within the same block, when we average up and we are at scale, we will combine more quickly. We will converge faster to the average grade. Whereas in high continuity, there is a good separation between low and high grades. So high grades will remain high grades when we upscale them. So, conclusions. So the change of support problem remains a difficult challenge. particularly when the data is scarce and the correct variogram is unknown. We have seen how the smoothing of kriging will distort the great tonnage curve in a great measure, quite similar to what the change of support will do, but sometimes can be way too much smoothing of kriging, especially if we apply them block kriging. But block kriging doesn't result in a huge change compared with just the smoothing effect of kriging. We have seen different change of support models and also simulation. So these methodologies can be used to benchmark kriging estimates and adjust estimation parameters to be able to better approximate the correct rate and tonnage curves. However, whatever the method used to assess this change of support effect, either change of support models or simulation, the results will remain heavily dependent on the quality of the variogram model. And the quality of the variogram model are related to the quantity and also quality of the data set we have. And of course, behind all that, in the background is the geology. If we have good domains, we are able to discriminate between domains that are statistically and geologically consistent. We will have less noise in our data. I haven't talked about uniform conditioning. I think it's something that should be mentioned, but I just have time to say about uniform conditioning or local uniform conditioning, that if it's well done, it should reproduce the discrete Gaussian change of support model when we are plotting the rate of tonnage curves. So should be the results of local uniform conditioning should be pretty much similar to the black lines we see here, because that's the aim of uniform conditioning, reproducing the change of support curves results. So with that, I'm open to questions. I think there is some question. There is one here. Yeah, is this a haircut diagram on the left side of the slide? Yeah, I didn't see that. Which one? Which slide? I think
it was the first slide.
The first slide. I don't know which slide was that. Well, yeah, it's a HERCO is known as it's a software that's quite known, well known. I don't use it, but I use other softwares. But HERCO comes from Hermite coefficients, and it implements this thing, the discrete Gaussian model. And that's, yeah, that would be the result of HERCO. But I use another program that's called just EGM, discrete Gaussian model. Yeah.
Okay. Thank you, David. The microphones are open if someone from the audience would like to ask a question directly. Please go ahead now. Well, in the meantime, if someone wants to, we have just another 9 or 8 minutes before David has to go. So David, in your practice, you apply always this change of support correction models, or
Yes.
depends on the data set?
No, I always try to use it, even if the data set is scarce. And actually, I use the change of support model to fine-tune my rigging parameters, such as the minimum and maximum number of data, when I'm doing long-term models. And I'm doing short-term models, such as monthly models or control. What I recommend, I don't know too much of those, but what I recommend is apply the QKMA. But QKMA can be misleading for long-term models, and that should be a part of another talk. It's quite interesting how the QKMA can mislead the long-term models, and actually conditional bias is not a bad word. It's sometimes it's good.
So in your practice, when you go and do the categorization of resources like into indicated and measured, would you consider this as a guidance or as something that gives you confidence in your model?
That's a good idea. Actually, I haven't considered that. I don't use that directly. I use that for validating and fine-tuning my estimates. But that's a good idea, Alan. Yeah, I think if we can separate blocks that are estimated, let's say, with high confidence in the first passes, from blocks that are estimated in the third pass, let's say, and we apply this change of support analysis, we can. I'm trying to figure out, but I think we could figure out what a certain measure of risk or in this different blocks estimated with different data quantity and proximity, and that could be used for substantiating or for supporting classification. But yeah, I think the idea is good, but I'm not sure. I need to think about a procedure to do it. Yeah.
Okay.
Thanks, some clues on how to do it. Yeah.
So we have another 5 minutes. Is someone please go ahead now?
Okay, there is another.
Yeah.
Yeah, there is a. Yeah, Stephen Ranger is asking, would this model be suitable for placer gold deposits, which are inherently quite variable in most deposits and sometimes difficult to estimate? Thank you. Yes, anything that can help us to get a more realistic grade tonnage curve is suitable. No method is perfect, as you can see here. The discrete Gaussian model approximates better the correct grade tonnage curves, but depending on the data quantity and also quality, we can improve the results. So we have a data set that sampled at shorter distances than the spatial the variant range, so it works. We have a quite tight data set of distances that can provide a nice variogram. I've seen that this provides a very good approximation of the correct grade tonnage curve. So here, my data set is quite bad. You see, I don't have many samples that are in this slope of the variogram. I don't have my points that are in the slope of the variogram, and I'm just inferring the shape of the variogram there. Does this provide any guidance to choice of block sizing practice? Hi, Linking. Nice to see you. Yes, Linking. Yeah, nice to hear from you. Yeah. Yes. Yeah, the change of support. Let's see this change of support. Let's see this correct group. Yeah, we don't know the true grade, so let's forget about the red line at this point. And we can, maybe not this one. I have another here. I have another. Oh no. Yeah, this one. Yeah, this one. these curves. And we can approximate these curves using the change of support methods for different block sizes. And for the sake of argument, let's say that these curves were approximated using change of support. I just did for 50 times 50, but we can do it same for times and 10, times 10, and etc. So with that, we can use to select, let's say, we are between 10 times 10 and 50 times 50. This change of support curves can let us help us to decide if we can afford to have a bigger block. So in this case, let's say our cutoff is 200. In this case, a bigger block, actually will increase the recoverable metal a little bit. So then we can go bigger. But depending of the cutoff too, the cutoff would be 600. It's not a realistic cutoff, but just for the sake of argument. And that will be a bad decision to go from 10 times 10 to 50 times 50. So it's this change of support can help us to decide between the block size and depending on the cutoff. Okay, Evangelis, is it possible to keep a small blocks don't change of support where variability is too high? High grade areas and change of support only on low variability areas. Yeah, I've seen that idea before, but I've seen that more related to data density. In areas where data density is high, we can afford to go smaller. The idea is that Kriging estimates are more accurate when we estimate big blocks. But big blocks should be supported by data that's abundant data. So when our data is more sparse, we can afford to have more blocks, small blocks. I need to answer to the next question. Would it make sense to reduce the parent block size during training estimate to increase between block variance, which would then produce a better Kriging efficiency, as well as higher block variance? Is there a limit down to which parent block sizes could be reduced apart from the plateaued results and or computational capability of minimum size, which could be allowable in line with QNAA? Okay, so let me see. It's a quite complex question. No, I'll answer. This will be the last one, but I need to.
I know because I know you have to go. It's 5 o'clock.
No, no problem. But this
okay.
This question needs to be answered.
Thank you. Yes.
Yeah. Okay, Marius. Let's see. Yeah. Okay. Yeah, the small blocks. Are prone to very clean efficiency. But it depends. It depends a lot of the quantity, again, the quantity of data and the quality of your body. If you have a good body, you can reduce the parent block size and therefore even improve selectivity. Regarding the limit down to which parent block size could be reduced, well, the thing is that if you don't have data that's closely spaced, there is no point to go lower than that. You will have quite similar estimates from block to block if you don't have data that's closely spaced. only if you have very closely spaced data, makes sense to reduce the current block sizes. Of course, a part of the computational capabilities, constraints, etc. Yeah. And that will be my answer to Marius. Yeah, thanks, Vangelis. Okay, glad to. Yeah, you found this interesting, and keep an eye for the second part, the information effect.
Yes, David, thank you so much for this very interesting and in-depth topic of geostatistics. So please, to all our audience, if you have any questions, you can contact David. Well, we can share your information.
Yeah, I forgot to share my.
I suppose it's in the last slide.
Yeah, I forgot to put in last slide. I have reference, whatnot.
Yeah. Yeah, David is in Mining Match, and you can contact David over the network.
Oh no, I put the wrong reference here. The last one is not mine. It's not the reference. There's another one that I wrote about change of support. That was the last slide I did. I was in a rush. I put the wrong one. Okay. All
right, David.
Yeah. Okay.
Thank you so much for your time.
Thank you. Thanks to everyone for your time too. That's more people than expected. I didn't expect to have acquire so much interest, but I'm glad. I'm glad that many came. Yeah. And there will be a Spanish version of this presentation.
Yes, so we will be communicating everyone about the Spanish version.
Yeah.
Okay.
Okay.
Yeah, you can stop sharing your screen, please.
Okay, I'll do.
Right. Yeah, we only have like 50 people online right now, but thank you, David.
Okay. Yeah, thanks to you, Alan, for the opportunity.
Yes, thank you so much. All right, so we reconnect next time in Spanish. Thank you so much.
Sure, next time. Okay, have a nice evening, everyone.
Same to you. Thank you.
Bye-bye.
All right, everyone. Thank you so much for coming. And as you know, the Mining Match is a space for you. So please share, invite others, and we keep sharing what we know among mining professionals. See you next time. Goodbye.